Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
the atmosphere is essential to all life on Earth. What is the atmosphere made of, and how was it formed in the first place? How has our planet's vital supply of air changed in the past, and how is it being threatened by human activities today? Today, scientists are unlocking these and other mysteries as they probe our atmosphere, the precious envelope.
What does it take to sustain a human being capable of driving a truck, or composing a string quartet, or making a new chemical? Well, let's pare it down to essentials. In one day, what it takes is about 2 kilograms of fresh water, about 1 kilogram of nutritious food, and 16 kilograms of air inhaled. We usually don't think we breathe that much air, but we do. About 1/5 of it is oxygen that we use. The rest, nitrogen, we mostly exhale. That materials balance is instructive in a number of ways. But what I find in it that is strongest, that comes across most directly, is that it tells me something about the incredible dependence that we have on the air, on the oceans, on the earth under my feet. We are sustained on the surface of a planet that is surrounded by a precious and subtle twin atmosphere of air and water that in a thin layer, only 10 kilometers out of the 8,000 from the center of the Earth, supports incredible life.
The Earth is unique. Of all the planets in the solar system, it is the only one with an atmosphere capable of supporting life. This thin membrane not only provides all life on Earth with a steady supply of essential oxygen, but it plays other important roles too. In synchronization with the oceans, the atmosphere brings us the climate and weather that are responsible for our planet's cycles of life. And often, to our dismay, dramatic changes in atmospheric conditions bring weather not to our liking. Without a canopy of air, there would be no seasons, airplanes could not fly, and fans could not cheer at a ball game. The Earth's atmosphere consists of various gases. The major ones are displayed here in their relative proportions. Nitrogen, which is essentially inert, makes up 78.1% of the atmosphere. Oxygen accounts for 20%. Other gases are argon, a little under 1%, and much smaller amounts of carbon dioxide, neon, helium, krypton, xenon, and hydrogen. Still more gases, not shown here, are present in varying concentrations, such as high-altitude ozone. These all form the gaseous mixture we call the atmosphere. Without this vital membrane of air, our planet would be as lifeless as the moons of Jupiter. So it is ironic that, since the advent of the industrial age, humans have been pouring unprecedented amounts of pollutants into the sky. The thin and protective membrane of high-altitude ozone is especially at risk. This delicate ozone layer lies 15 to 40 kilometers above the Earth's surface. Molecules of ozone, made of 3 oxygen atoms, block a large portion of the sun's potentially harmful ultraviolet radiation. So the ozone protects life on the planet. Dr. Robert Watson is Chief of Atmospheric Sciences for the National Aeronautics and Space Administration.
The main importance of the ozone layer is it screens the harmful ultraviolet radiation from the sun from penetrating to the surface of the Earth. If there was less ozone in the Earth's atmosphere, it would mean more ultraviolet radiation would reach the Earth's surface with potential adverse consequences for both human health, such as skin cancer, both melanoma and non-melanoma, and probably would have adverse effects on the productivity of both aquatic life and terrestrial life.
But the ozone layer is threatened by synthetic substances called chlorofluorocarbons, or CFCs, that rise into the upper atmosphere. CFCs are used mostly as coolants in air conditioners and in refrigerators, not only in the home, but in large refrigeration systems used to transport perishable food worldwide. CFCs also are used as solvents to clean computer components and for manufacturing styrofoam. Robert Schrubar is Environmental Coordinator of the Freon Products Division of the DuPont Company, the world's largest producer of CFCs.
CFCs were first developed in the late 1920s, early 1930s as replacements for the more toxic or flammable refrigerants. The idea was to have a safer refrigerant for use in your refrigerator at home or in similar machines that are used around the general public. The market value of CFCs in the U.S. is on the order of $1 billion. Worldwide, it's about 3 times that much. Products or services related to CFCs in the U.S. are about $27 billion.
During the 1970s, a peculiar depletion of ozone was detected over the South Pole. It was the first clue that something was wrong. By 1985, the Antarctic ozone hole had doubled in size. This image of the globe is taken from a satellite directly above the South Pole. It shows the black ozone hole changing in size. In 1987, Dr. Watson and other scientists used high-altitude research craft, such as this ER-2 plane operated by NASA, to take air samples above Antarctica. These flights confirmed what they already feared, that the size of the ozone hole was increasing at an alarming rate, although it still seemed to be confined to the atmosphere over Antarctica.
I was the mission scientist on the DC-8, which actually flew over the South Pole. It was the urgency of the situation that convinced all of us that we had to go down there and devote many months of our lives just to understand what this particular campaign was all about, and specifically what was causing the ozone hole. I've been concerned for many years that even small changes in ozone could be detrimental to human health and to the aquatic and terrestrial plant life on Earth. But when we suddenly see a 50% change in ozone in only a 10-year period from 1974 through to the middle 1980s of 50%, one has to be concerned. One has to ask the simple question, what is causing the Antarctic ozone hole? And even more importantly, will it spread globally?
Here is a model that describes how ozone might be destroyed in the upper atmosphere. A chlorofluorocarbon is released into the atmosphere from the Earth's surface. As the CFC molecules rise into the upper atmosphere, they are bombarded by ultraviolet light, breaking loose a single chlorine atom. The single chlorine atom, in turn, reacts with an ozone molecule, breaking it apart. This creates a molecule of ordinary O2 and a molecule of chlorine monoxide. Free oxygen atoms exist in the atmosphere, created by the action of light on ordinary O2 and ozone. This molecule of chlorine monoxide is broken up when it reacts with a free oxygen atom. This creates O2 and a free chlorine atom. The chlorine atom is then free to attack ozone molecules again. This is a chemical chain reaction. For every chlorine atom released into the atmosphere, thousands of molecules of ozone are removed. Evidence shows that the depletion of ozone is spreading worldwide. A 1988 NASA report indicated that there has been a measurable reduction in ozone levels in the northern hemisphere.
That information prompted DuPont to be consistent with its environmental policy and to come forth with our new position where we set as our goal the orderly transition to a phase out of the fully halogenated CFC production.
Although the full story about ozone depletion is not yet in, chemical manufacturers like DuPont are developing alternatives to CFCs that will not damage the atmosphere.
The alternatives that DuPont is developing or that DuPont has announced are all in the fluorocarbon family, meaning they contain carbon, fluorine, some contain chlorine. They also would contain hydrogen. And it's those combinations of elements that give the compound its stability, while at the same time, if it has chlorine, it needs a much shorter atmospheric lifetime so as not to affect stratospheric ozone. The addition of a hydrogen atom will cut that atmospheric lifetime drastically.
This is DuPont's Chambers Works, where many chlorofluorocarbons are now being made, soon to be replaced by we don't know what yet. Let's come back to ozone, that wonderful gas which in the upper atmosphere protects us from ultraviolet radiation. Here down at sea level, that same molecule is a very nasty actor indeed. It's a blue gas with a characteristic strong odor. It's generated around electrical discharges, and we can smell it in concentrations as small as 1 part in 100 million. It ruins tires, damages plant life, and is a component of photochemical smog. And in another context, it's sometimes used to purify water. The moral of the story? There are no clear heroes or villains in the molecular world. There are only molecules in equilibrium with other molecules. The heroes and villains can only be human. The heroes, for instance, are those people who have puzzled out with ingenuity and with sweat the mechanisms of ozone depletion, or who, acting by themselves or in concert with others in society, are willing to modify their ways to preserve this atmosphere.
How do scientists learn more about the threats to the atmosphere? One way is to study how this precious envelope of air evolved over billions of years. Scientists believe that when the Earth was in its infancy, there were many volcanoes, far more than today. Energy produced by radioactive decay deep beneath the surface melted rock and forced lava and gases upwards toward the surface. Lighter gases, like hydrogen, escaped into space. Denser gases were held near the Earth's surface by gravity, forming a primitive atmosphere. There also were vast quantities of water vapor which, because of strong intermolecular forces, eventually condensed to form the oceans. How did the primitive atmosphere and the early oceans evolve together to produce life on Earth? Probing for that answer may help us understand how these systems stay in balance and how human activities threaten nature's exquisite balance. One of the best-known researchers in the field is Dr. Cyril Ponnam-Paruma.
What we have here is an apparatus that gives us an idea of what could have happened on the primitive Earth 4.5 billion years ago.
The upper flask represents the primitive atmosphere, while the lower one represents the ocean. The early atmosphere was made up mainly of methane, ammonia, and water vapor. This sidearm is kept warm, while this condenser is kept cold. Water vapor rises through the warm sidearm to the upper flask, much like water evaporating from the ocean, and it falls back through the condenser as if it were rain. This electrical discharge simulates lightning through the primitive atmosphere. When the lightning discharges, a number of reactions take place that could result in the formation of organic matter, which collects in the ocean below.
Students of chemical evolution who study the origin of life call that the primordial soup. It is believed that the early oceans had an accumulation of organic molecules, the very building blocks of life. Amino acids, the bases that occur in the nucleic acids. In this laboratory, in this very experiment, we have synthesized all 5 of the genetic bases. Here we have a wonderful way of simulating the atmospheric conditions of the early Earth.
With the building blocks of amino acids in place, primitive life could begin to develop. First, as single-celled organisms originating in the primordial soup of the sea. Later, as more complex and adaptable organisms capable of leaving the water and living on land. Gradually, some organisms developed the ability to release oxygen into the atmosphere. And from then on, life could begin to evolve in more complex forms, which in turn helped produce more oxygen for the atmosphere. To predict how the atmosphere might change in the future, scientists today try to discover how it has changed in the recent past. One way to measure these changes is by taking samples of tree rings that reflect climatic changes over centuries or even thousands of years. Atmospheric scientists also can track past changes by taking samples of buried ice that formed on the surface long ago. By testing such samples, scientists have shown that the Earth was a little warmer about 1,000 years ago, and from the 16th to the middle of the 19th centuries, it was about 1 degree Celsius colder than it is today. For an even deeper look into the past, scientists sample layers of sediments that have settled on the floor of the ocean. Scientists also monitor subtle but significant changes occurring in the atmosphere today, since these changes have the potential to enhance life or seriously disrupt global cycles. One of these cycles is called the hydrologic cycle, the constant movement of water, evaporating from Earth to sky as water vapor, and from sky to Earth as precipitation. The hydrologic cycle has existed for millennia. It's even possible that when you take a drink of water, you may be swallowing a molecule or two once drunk by Julius Caesar. Powered by the heat of the sun, this slow but steady cycle of evaporation and precipitation is always in balance for the Earth as a whole. About 10% of all precipitation falls on land and provides us with the supply of fresh water that we depend on. In the laboratory, series demonstrator Donald Showalter shows how carbon dioxide plays an important role in another cycle vital to life on Earth.
This is bromothymol blue, a nice pretty blue color. Remember the blue. Now, this acid-base indicator will change color if there is a change in the acidity of the solution. Let's add some of our carbon dioxide, the dry ice, and see what happens. We notice the dry ice bubbles. Oh, look at that. There's a color change to this beautiful yellow color. Now, what does that mean? Remember, we said this is an acid-base indicator. So the carbon dioxide not only dissolved in the solution, but it also changed the acidity of the solution.
Photosynthesis by plants also depends on carbon dioxide. An experiment with bromothymol blue demonstrates this vital role.
I have 3 test tubes here that are filled with water. And then I saturated them with carbon dioxide. Just dropped it in there and let it bubble away. I also put some indicator. Remember that same indicator, bromothymol blue. So it turned yellow. And then I put a water plant in 2 of these. Now this is actually the experiment here. We want to see if the plant will absorb that carbon dioxide. And then the acid content will decrease and we will see a color change if it happens. What I'm going to do now, I'm going to take this tube with the plant and this one over here without and expose it to an intense light source. I'm going to take this tube out in front here with the plant in it and put it into a dark area where it's not exposed to light. Now what do you think is going to happen? Well, there's going to be some change, huh? We hope because of the absorption of the carbon dioxide. But that's going to take quite a bit of time, certainly more than a day. So I can't sit here and let you watch it while it happens. I've already done that for you. Now let me show you what happens. After at least 24 hours now, look what's happened. The solution has turned blue. Now that means that this water is now less acidic, right? The blue color means less acidic. What happened to the other two, though? Now, remember, this one was in the dark. Didn't have any light exposed. And it didn't turn color. And this one now has no plant in it. It was exposed to the light, but it didn't turn color either. Okay, now what does this all mean? It means now for the plant to absorb the carbon dioxide, we need to have the plant, we need to have water, and we need to have light. And if all those are present, the carbon dioxide will be absorbed and the solution will be less acidic.
Carbon dioxide's ability to dissolve in water and its reaction with plants are part of what is called the carbon dioxide cycle. Much of the carbon dioxide gas released throughout geological times by volcanoes, and today by respiring animals and plants, is dissolved into the ocean. In water, carbon dioxide forms a bicarbonate ion and a carbonate ion. Some of these end up as calcium carbonate, an insoluble compound found mainly in plankton whose skeletal remains eventually settle to the ocean floor. Photosynthesis is an important part of the carbon dioxide cycle. Green plants use solar energy to convert water and carbon dioxide into glucose and oxygen. Oxygen is released into the atmosphere in enormous quantities. So as long as there are plants and sunshine on Earth, there will be a never-ending supply of oxygen in the air. It has taken eons for the atmosphere to evolve. But as our experience with ozone has shown, only a short time for humans to disrupt this precious envelope. Since the Industrial Revolution began over a century ago, massive amounts of coal and other fuels have been burned. Unprecedented amounts of carbon dioxide have been pumped into the atmosphere. Today, our species is an agent of nearly geological magnitude. In addition to producing CFCs in vast quantities, another way human activities may be changing the atmosphere is through a mechanism called the greenhouse effect.
We're concerned that through the greenhouse effect, the Earth's system may warm up by only a few degrees, 3 to 5 degrees during the next few decades. If there were to be an increase, even of only a few degrees, the concerns we have are simply there might be an increase in sea level, erosion of the coastal areas, there may be change in precipitation patterns, there may be a change in the severity of storms. For example, certain models would predict that the American Midwest may become quite dry. It will go back to the Dust Bowl of the 1930s, wheat will not grow efficiently there. Whereas the warmer temperatures in Canada and the USSR will mean that there will be far more productivity of grain in the high northern climates. One could envisage under one scenario, very simply, that instead of America being an exporter of wheat, it may become an importer from countries such as Canada and the USSR.
Here is how the greenhouse effect works. The atmosphere allows most visible and ultraviolet radiation from the sun to penetrate to the surface. Thermal radiation is emitted from the surface and absorbed by molecules of atmospheric gases such as water vapor and carbon dioxide. These molecules serve as energy banks, releasing energy in the form of heat and making the Earth habitable. But this greenhouse effect can become too strong if excessive carbon dioxide accumulates in the air, trapping additional heat and raising the temperature at the surface. As a result, the mean global temperature has risen about 1/2 degrees Celsius during the past century. To review, current evidence indicates that our atmosphere developed initially from gases pouring out of volcanoes. The oceans formed as water vapor condensed from the early atmosphere. A series of cycles, such as the hydrologic and carbon dioxide cycles, maintain the ongoing relationship between the atmosphere and the oceans. Photosynthesis is part of the carbon dioxide cycle and provides life-giving oxygen. The possible depletion of the protective ozone layer is one serious threat to the atmosphere today. Chemists are developing substitutes for the CFCs that seem to be damaging the ozone. An increase in the greenhouse effect caused by an overabundance of carbon dioxide in the air is another danger to our planet. The atmosphere is absolutely essential to life on Earth. This precious envelope must be protected at all costs.
Okay, let it go. We use weather balloons like this one to probe what goes on in the atmosphere. And what goes on is not just a function of local weather patterns, but of all those global cycles. These marvelous cycles on carbon dioxide, on water, they are actually examples of something more general, what we might call budgets, global balances, telling us how the elements and compounds are distributed on the Earth, how they are transformed, how they are conserved. You might think of other balances of this type, on phosphorus, on sulfur, on nitrogen, on iron, on other elements essential to the Earth. These global cycles reflect the equilibrium that the Earth has reached. It's an equilibrium that has evolved with time. And then we came. When we were few, it didn't matter. But now we are a multitude, and our tools enhance the effects of what we do.
Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.